Hey everyone, and welcome. We're about to pull back the curtain and look at the hidden machinery that makes, well, everything on your computer actually work. Let's jump right in. Have you ever really stopped to think about it? You click an icon on your screen and, poof, a whole complex application just appears. It springs to life. But what is that invisible magic, that force translating your simple click into a running program? Well, that's exactly the question we're going to answer.
And the answer, believe it or not, has a name: systems programming. You can think of it as the foundational layer of everything. It's the critical bridge between the apps you use every single day and the actual physical circuits and silicon inside your machine. It is quite literally the engine under the hood.
All right, so to really get a grip on what systems programming is, sometimes it's easier to start with what it isn't. So let's draw a line in the sand and separate the software you see and touch from the stuff working tirelessly behind the curtain.
Okay, so you've got two totally different worlds here. On one side, you have application programming. This is probably what you think of when someone says coding. It's using languages like Python or Java to build the apps you actually use, your web browser or photo editor, you name it. But on the other side, you have systems programming. This stuff is way more low-level. We're talking languages like C and C++, and their job is to build the operating system itself, or the drivers that let your computer talk to, say, your printer. It's all about controlling the hardware directly and managing resources as efficiently as possible.
And, at the very heart of all of this is the single most important piece of system software there is, the operating system, or OS. I love this analogy. If your computer is a massive orchestra, the OS is the conductor, making sure every single part plays together in perfect harmony.
Yeah, the OS's job is to manage, well, everything. It decides who gets to use the processor and when, how all the memory gets divided up, how to talk to your keyboard or your screen. It basically creates this beautiful, simplified layer of abstraction. And that's huge, because it means the person writing a web browser doesn't need to know the super complex, specific commands to draw pixels on your particular screen. Nope, the OS handles all that translation for them.
Okay, so that raises a question, right? How does your web browser actually ask the OS to do something, like save a file? It can't just reach into the OS's brain and do it itself. That would be chaos. Instead, it uses this special secure bridge. And that bridge is called a system call. It's the official, formal way a program requests a service from the kernel, which is like the absolute core of the operating system.
You can think of these system calls as the basic verbs in the language that apps use to speak to the OS. You've got commands to open a file, read from it, write to it. Every single time you save a document or load a web page, these fundamental system calls are firing off like crazy in the background, completely hidden from view.
All right, so we've got apps talking to the OS, but wait a minute. How does the OS keep track of all these different programs running at the same time? You might have your browser, music, and a game all going at once. Well, that brings us to the next piece of the puzzle, the super important concepts of processes, threads, and memory. So, the moment you launch an application, the OS creates something called a process. A process is basically just a running program, and, this is the important part, the OS gives it its own private, totally isolated sandbox of memory to play in. And that isolation is everything. It's the reason why a crash in your web browser doesn't take down your entire computer with it. Thank goodness for that, right?
But then what if different parts of the same program need to work together on the same chunk of data? That's where threads come into play. See, unlike processes, which are walled off from each other, threads are these lightweight little workers that all live inside a single process. And the key difference? They share its memory. This is exactly how modern apps can do multiple things at once, like playing a video on a web page while the rest of the page is still loading in.
And this memory space that each process gets, it's not just a chaotic jumble of data. Oh no, the OS is a master organizer. It lays everything out super neatly. There's a section for the program's actual code, another for its permanent data, and then two really important areas. You've got the stack, which is like a short-term memory that keeps track of what the program is doing right this second, and the heap, which is a big pool of memory the program can borrow from whenever it needs extra space. It's a beautifully organized system.
So, how do people actually write this incredibly powerful, low-level software? Well, you can't just use any old tool. You need special languages for the job, languages that can speak almost directly to the machine itself.
The classic powerhouse, the grandfather of them all, is the C programming language. It's famous for giving developers raw, unfiltered power and direct control over memory. Then you have C++, which takes that foundation and adds a bunch of more modern, object-oriented features on top. And for those times when you need to get as close to the metal as humanly possible, speaking the CPU's native tongue, that's when you pull out assembly. These are the go-to tools when every single nanosecond of performance counts.
But hold on, there's a pretty big gap here, isn't there? We write code in a language that looks kind of like English, like C. But the processor at the heart of your computer only understands one thing, ones and zeros, pure machine code. So how do we bridge that gap? How does our human-readable code become something the machine can actually understand?
Well, it happens through this amazing journey called compilation. It's a multi-step process. First, something called the preprocessor does some basic text cleanup. Then, the real magic happens. The compiler translates our high-level code into that more primitive assembly language. Next, the assembler takes the assembly code and turns it into the actual ones and zeros, the machine code, creating what are called object files. And finally, the linker acts like a master puzzle solver, pulling all the different pieces together, along with any external libraries, to create that single, final, executable file that you can actually click on and run.
Okay, wow. So we've gone pretty deep into the technical weeds here. But you might be asking, why does any of this matter to me? And the answer is, it matters a lot. Because this hidden world of systems programming directly impacts your digital life every single day, in ways you probably never even realized.
Just think about it for a second. Every single fast-paced video game that runs smoothly, every operating system that doesn't crash on you, every secure online purchase you make, every one of them is built on a foundation of expertly written systems code. This stuff is the bedrock of performance, the backbone of reliability, and truly the front line of our digital security.
Let's put it this way. Without solid systems programming, nothing else works. It's that simple. It's the platform that enables all other software to even exist. It's our best defense against critical security flaws like buffer overflows. And, at the end of the day, it's the engine that drives the incredible speed and efficiency we've all come to expect from our tech. So, the next time you tap an app, swipe a screen, or click your mouse, maybe take half a second and remember that incredible invisible world of systems programming that's working tirelessly just beneath the surface. It's this complex, elegant, and unbelievably powerful foundation that makes all of our simple, everyday digital interactions even possible.
Because once you understand how the foundation is built, you start to see the whole structure differently. You realize it's not just magic, it's truly brilliant engineering. And that really leaves us with one final exciting question. Knowing what's going on under the hood, what amazing things can we build on top of it next?